action.
So now I'll turn it over to Ken. He's going to talk about small-scale autonomous racing cars.
Thanks a lot. I want to tell you about my journey over the course of a little over a year of building these two particular cars. And specifically, the project goals that I had is I wanted to make something autonomous. I wanted to use inside-out localization. So anybody familiar with that, it's essentially just having a camera point out the front of it and be able to see the line and understand where the map is, do localization in that particular way. Not have something external from the car, reading where it is, like GPS or something like that. I wanted to be fast, so 15 meters per second, it's 33 miles an hour. That's about the speed of a cat. The agile, I want to be able to pull about a G, which is about a cat. And I wanted to be small, about 1/12 or 1/10 the scale of a car, which is also about the size of a cat. So for me, I'm thinking of this talk more of I spent a year working on this stuff, and I went down some paths that turned into dead ends. I went down some paths that turned into huge, evolution for the next car. This is incomplete, so I'm still in the process of putting this together, and I want to share everything that I have. But some of the topics that we're going to talk about are listed here. So you can see the cars here, but the past is a car that I cobbled together with whatever parts that I had around the house. And the latest version is something that I specifically picked out the parts based on everything that I learned from building the first one. I highly recommend that if you want to get in the hobby, get a donkey car, drive the heck out of it, and learn what you can out of just having something first. And then figure out what works for you, what you think is the next evolution in the process. So the Mark I system, so that larger one, was a Raspberry Pi connected to an Atmega, essentially an Arduino Nano, but I wasn't using the Arduino piece of it. It's very easy just to use the boards as just to be able to build on top of it. I thought in the beginning that having an actual remote would be useful when I'm actually doing training and driving the car. I wanted to kind of make sure that the odometers can actually read at the speeds that I wanted to drive. I wanted to do some aggressive driving and record that telemetry. I built it using just what I had available for a DC, electronic speed controller, and that turned into a thing where with a DC motor, you need to run 2 different batteries because the power supply is pretty heavy duty. I had, in this case, built the actual encoder. So this is just a rat mess that I cobbled together very quickly to get something kind of driving. The encoders were just something that I cobbled together again with just using some 3D printed holders for some sensors and just a quadrilateral encoder that I had on the half shafts. If you're getting into the hobby, you're going to need some tools. I would recommend, if you can, a very simple desktop mini mill does really, really well. For me, this is something that you can pick off like eBay for less than $400 if you price it out correctly. But in this way, you can build very small parts, very precise parts with something like this using Fusion 360, or if you're going to build something very quickly, you could just use a 3D printer. And I end up using both of those manufacturing techniques back and forth. The other thing, when I was actually playing around with this, is making sure that the actual hardware worked the way that I expected it. And so actually being able to hook up the half shafts to an actual stepper motor and using Gerbil to just do some motion control and actually count the steps and make sure that the software was working the way I intended it to work is something that I absolutely kind of recommend as you're going through the build process to make sure that you qualify everything you're actually doing and you're not just basing it on, well, I pushed it 10 feet, I think it did the right encoding counts. If you can actually qualify it, it works out really well. So I'll show you simpler approaches to this, but essentially just using Gerbil with a stepper motor controller worked out really well for me in this particular case. So this is going to be a dead-end path, all right? I went down the path of omnidirectional cameras. I think they're cool. I think there's more experimentation that can be done. I think they're very applicable to a robot like that little vacuum robot there. excuse me, the bot vac?
Nito bot
The
vac.
Nito bot vac.
No plug there.
In the situation where you could potentially use 360 coverage and the further range, but I want to tell you that, you know, off the cuff, that this was a dead end for me, and I'll tell you why. So, one of the things that I saw immediately, because I was thinking, you know, I want to race this car, I want to be able to go down the path. I think I need to be able to look left and right and behind me, because I'm going to be racing cars, so a 360 cam would be great, omnidirectional camera would be great. And I just searched for, you know, Raspberry Pi and omnidirectional camera, and I came across Catherine Scott's blog post where she just took a Contigo lens that you can get off of eBay right now. It's a discontinued item. She wrote just a very simple dewarping piece of kit. And I was impressed by this. I thought it was an interesting way to kind of roll. And it's cheap. You know, for $9 you can get one of these lenses, a little bit of 3D printing. I can give you guys the 3D files if you'd like. And I had a omnidirectional camera mounted on my system, and it was cool. The initial piece that I immediately kind of saw is that you lose a lot of your field of view. The sensor utilization is very low, because the only thing that's useful is this donut in the middle. And for the Raspberry Pi, you're best kind of switching down to mode 6 on the actual mode 6 on the actual capture side of things. So on with, you know, what I was able to read on Catherine's blog and just playing around with the kit itself. I wrote some tooling to actually do the basic alignment. And basically you can see me just moving this kind of reticle around and just aligning it by hand, just by eye. Didn't have a calibration mechanism yet, but I just wanted to get something going so I can actually go further and do some further testing with things. So here it's almost aligned in there. There's 3 pieces here. So the donut is what we're actually seeing. The actual panoramic isn't particularly useful, but it's this disc that I have, this very small resolution disc, that I have that I thought was useful for a particular technique, and I'll show you in a second. But it is basically everything below the horizon underneath the car, essentially. So I, as a segue, really easy way to get video telemetry, video and telemetry on the Raspberry Pi is to actually use a piece of kit called GStreamer. If you're doing any kind of video manipulation, or you want to stream it over the network or anything, GStreamer is a great, both a command line tool set and a library that you can essentially cobble together whatever pipelines that you want for putting together video. And in my case, I was able to use an app sync on the actual video stream and collect all of the data that I was getting over the I2C bus from the AppMega 2 and the IMU, and put that in as key value pairs to an MPEG TS stream, and can capture essentially the entire run of my car as I'm driving it around. At high speed, I can capture all of the video and the telemetry and then replay it over and over again. Very much like ROSFizz, but in my case, I kind of wanted to understand a little bit deeper and not use the ROSFizz as or ROS as a tool set. I certainly wanted to understand it a little bit more. This is a very simple way to get that telemetry capture. The other thing that I did on the first car, not the second, is I implemented a remote. I actually think that the gentleman with the with your robot, you're actually doing essentially what I'm about to explain. Using a remote, you can actually talk to a DR4 2 in my case, but the output of this is S-Bus. And S-Bus is a very simple serial protocol. It's 1,000 bauds, inverted logic, so the circuit on the left will take care of you. And you can plug that directly into an Arduino or the Raspberry Pi, 3.3 volts for the Raspberry Pi, 5 for the Arduino. But this allows you to get 16 channels out of your remote. It's super simple, and you can get off the ground, and in my case I only use 2 channels. My remote was capable of 16 plus a couple of these little switches on the back. I'm sure in your case you're planning on using a lot more of those. Another consideration, and something when you're driving your car around, specifically at high speeds, it's great to have a calibrated space, and a painted basketball field is perfect for that. In my case, this is something relatively close to my house. I'll show you driving around this particular course, but from having a calibrated space that I could go and get a sense of where I am on that basketball court is super useful. So again, I was using the disk of that image that I calibrated previously. And here's the robot just doing, oops, the wrong one. Let me go back, there we go. All right, so this is a run around that basketball court that I just showed you. You can see my sons running around in the background trying to chase after things. But here I'm stamping out each one of those disks using the odometry data, the actual IMU. And the concept that I had for basic localization was going to be essentially a slam, where I was trying to meet each one of those disks as I was traveling forward. But you can see how it actually painted out the what is that, the paint in basketball terms. It's about to cross over the paint on the other side of the court and cross over. This gave me a bunch of data immediately. How fast I thought things were going, whether or not my encoders worked correctly, whether or not this was somewhat of a reasonable path. It also told me a lot about this omnidirectional camera. One of them is, you can see, it's very blown out. Like, things are very, very bright. There's not a lot of, things are grainy at the bottom. And I also have a bunch of kind of inclusions, like lots of lens flares that were running into this problem. The other thing about capturing, cool runs is that you can actually get some of the crashes too. So I'll show you one of those.
Oh yeah, I want to see that.
Yeah, Thanks everybody. So it's going to be real fast, but it's going to be fun. So this is me running after it, and I had stumbled with a particular EMI issue with this particular car where it would gun itself very quick, very fast, and then give you back control right at the last moment. Here I am running in the background after it, and whoa!
If you haven't crashed it, you haven't raced it. That's really
So this one, so if you imagine on the top of this camera, I actually went from the omnidirectional camera to a forward-facing camera. But if you imagine this, this actual attachment on top of that thing, that flip was perfect. It came up, it didn't hit the lens at all, and landed right back onto its, pretty much onto the front of itself and landed back down, didn't break anything. That was the last time I was given, that kind of favoritism by the gods. Hold on. Did it pop up? Okay, hold on. I want it to be full screen. There we go. All right, let me go back one. All right, so this is at the DIY Robocars, where I'm racing around a track, and you can get a sense of an omnidirectional car on a track. Again, I'm driving it, collecting data, trying to see whether or not this localization mechanism would work the way that I expected. Again, what you'll see is really bright lens flare. You'll see these lines here coming down. That would absolutely has tripped up other cars as being a line on the actual track. So something that I knew I was going to have to deal with. Also, they had, I think, halogen lamps or something of a different color, very yellow, so that you could actually have a reflection that was perfectly a fake line from the windows and a fake yellow from the lights, and it was just steering you off in the wrong direction.
You're driving this thing, are you training it?
So in this case, the idea was to get a first shot of how fast can I drive it, how can I do aggressive. So I'm not training it yet. That'll come a little bit later. So this was really just to get to a point of being able to vet the system, make sure that things work the way I think that they should work, that I'm able to kind of capture telemetry. This was essentially, a week or two after I built the car, I went off and drove it around and crashed it. All right, so this was my idea for localization, and the idea was to take two consecutive disks from T-1 and T0 and try to align them. So in the bottom right corner you can see this alignment here, and just doing a least squares error and finding where those two matched. And that generally worked okay, except for the problem of that line is actually supposed to be straight, and it's not. So my basic calibration that I did by eye is not good. So I knew I needed to do some calibration. I needed to figure out how to do the checkerboard, like a chessboard calibration. So that was the next kind of phase of it. So again, it pops me in every time. So I knew I need calibration. Calibration for an omnidirectional camera is not exactly straightforward. It's something that is now supported in OpenCV. It's something that I wanted to better understand myself. The particular lens, this is from their patent filing. The lens itself, I didn't realize this until afterwards, but there's a non-linearity between that top portion at the horizon and the bottom portion below. And I really only care about everything below. So it's far less of the actual field of view for the sensor than I wanted. So everybody should know chessboard calibration, but when I looked at it, I thought that this was overly complicated for what I wanted to play around with. Generally you do like a binary thresholding and use some complicated math. I thought, it would be best to try to do it like humans do. This optical illusion is a very good example of why the chessboard calibration problem is actually difficult. A and B is the same color, it's the same gray, but your brains, and we take for granted the ability to differentiate those two, even though that they're, you think that B is lighter than A, and it's not. That's something that you could train, with TensorFlow, and give it enough data. You can train those intrinsics into the program to actually find the corners that I want. So I started looking at papers and different ways to actually do a calibration. The thing that I was dealing with is, as soon as I put this particular thing into OpenCV, I didn't get a good result out because the image is highly distorted. It's very grainy and blurry to boot. So I started reading around, and David Scaramuza and team had a paper out for automatic checkerboard detection. And the thing that they were doing that I thought was very interesting is this whole idea of taking one set of thresholded images and then eroding the image and getting to the point where you actually got the corner pixels to align the way that you expected them. And I thought that was an interesting thing, but it was another analytical approach that I think we just do. And we should be able to train with enough data something that can actually find the corners without a bunch of kind of analytical approaches to very individual problems. I wanted to just get the corners out of an image. So what I did is I put together a convolutional neural net using TensorFlow that essentially just took 64 by 64 pixel images, grayscale images, with a very simple model. What I wanted to do is take that image and output the actual corners that I expected. There's a very simple algorithm called the Delaney triangulation that finds the smallest triangles within a set of dots. So I was okay with the Delaney triangulation, but all of the intrinsic about, you can tell in this particular image, if you stare hard enough, this actual white is very much more white than the gray up there. It's the same problem as that optical illusion before. So I took my car, spun it around with a checkerboard pattern, and I thought, great, I have training data, except I don't have labels. So you have, whatever data you have to actually know where the corners are, in my case. How was I going to get those labels? So then I started thinking about it. Well, I could just generate the checkerboard pattern, and then I can distort that checkerboard pattern, and I can just screw with it, mess with it. In this case, what I started doing is just using a piece of OpenGL that drew a checkerboard pattern and then passed it through a distortion. And I passed also the corners through the distortion, so I had both the actual training image and the labels for the training network. So in this case, you can start seeing it get a little bit better, and it's finding something. But after a fair bit of training, you can see these hotspots are all where it thinks a corner is. In general, the mechanism worked the way I expected, or I hoped. So this turns into something where, I can take an image from my super blurry image, have it pass through, it's very hard to see, but there's the dots around here, do the Delaney triangulation, and then superimpose what the checkerboard should be on the other side. And that's all done pretty much, well, not pretty much, entirely through just training a model and getting the data out of it. So it was, success, great. I have a chessboard pattern that I actually can play around with. Then I started looking at the omnidirectional camera. So I preface this, don't get angry. but I decided that, you know, the omnidirectional camera had a lot of downsides that I ran into. And I came back to these 4 things specifically. The resolution, for my particular situation, I want to drive really, really fast in the forward direction, and if the distance that I'm traveling is greater than the number of pixels that would fly forward, you know, this small little rectangle, then my vision system is too slow, it doesn't have enough resolution. Also, I don't actually